Here we go. So these are your buffers, and this is what 8.4 was, but I like to do the titrations and kind of save this for a little bit of the end when we've already talked about acid salts and basic salts and stuff like that. I think that this fits in better there, so that's why I flipped 8.4 over to here. Okay, so first you need to know what a buffer is. A buffer is a case where you have the common ion effect occurring, and we talked about that last unit. A buffer is a solution of a weak acid and its conjugate, or it may be a weak base and its conjugate. It is going to resist changes in pH. And we've seen that in some of those titration graphs that we've looked at, where we've had these weak acids at play. So this section right in here, do you see how the pH is changing very little? That's going to be a section where you've got a buffer occurring, okay? And as you're adding in more base here, it's resisting a change in pH. This is almost a zero slope, isn't it? And we're going to learn as we move through these notes the next few days why that is the case. Okay, so buffers consist of both the acid, an acid or base, and its conjugate, which is its complement. An acid and a base are present in all buffer solutions. If a small amount of strong acid is added to the buffer, there's a base component then waiting there to kind of neutralize it, and vice versa. So you kind of need to know a few things, right? You need to know the conjugate acid and base concept. So when we talk about that, if we're talking about HA plus H2O, okay, that's going to form A minus plus H3O plus. Everybody cool with that? This is an acid. This then is its conjugate base. This then is the base, and this is the conjugate acid. Do you remember talking about those earlier? The way you identify that is you find the two things that look like each other. See how those are related? The one with more hydrogen then is your acid. The one with less hydrogen is going to be your base. If it's on this side, it's called a conjugate. See how this and this look alike? This one has more hydrogen. That's your acid in the pair. Does that make sense? Okay. So you've got that vocabulary down. You need to know that pH equals negative log of H concentration. You're comfortable with that? We've been doing that for a while now. You need to know that Ka times Kb equals Kw. And Kw at 25 degrees Celsius equals 1 times 10 to the negative 14. Good? You need to realize that any titration involving a weak acid base is a buffer problem. If I titrate HA, so a weak acid, with NaOH, then as soon as the first drop splashes in, I've made this, which then, of course, becomes this. Because that's not going to stick together. The sodium is just going to break apart there. The sodium is very, very soluble. It's soluble almost all the time. Okay? The key to buffers is to memorize this. You need to commit this puppy to memory because it is not on your sheet. Now, what is on your sheet is this. So that's what's on your sheet. That's what they give you to work with. This is what we talked about yesterday, being that Henderson-Hasselbalch equation. This is what they give you. The way I teach buffers, though, which is much, much easier than this thing, is you have to have this. So you got to have this in your toolbox. So get this memorized, think about this, get it committed, okay? This is friendlier to deal with. You're not dealing with any kind of pluses here. So everything can be divided or multiplied out using my method, okay? And if you know this, you can easily get to pH just by doing negative log, right? If you know this guy, you can easily get to pKa, right? By just taking the negative log again. Okay? So you just have to have a little bit of trust in me to know that this is really the best way to go with this. Okay? So I know it's going to take a little bit of memorization. You might be able to, in your mind, take, whatever they give you on the sheet here. You can see that this is essentially just that up, and it's been flopped around. Because this is your acid, this is your base. Okay? So, if this is given to you, and if you can take that and kind of come to this, then you can work it out. Does that make sense? All right. But that is the key. You want to have this thing memorized.
So is that Ka multiplied by acid over base?
Yep, the ratio. Okay. So if an acid is added to a buffer, simply add the acid to the numerator and subtract the same quantity from here. But, okay, you have to subtract in moles, not in molarity. So you've got to convert these to moles first and then go back to molarity. I'll take you through it. Just trust me. Okay. When equal concentrations of moles of acid and base are present, okay, which occurs at the half equivalence point, the ratio of the acid to base equals 1. So when these are at that half equivalence point, the ratios here equal 1, and that's why your pH and your pKa equal each other. If you are asked to construct a buffer of a specific pH and given a table of Kas, choose a Ka with an exponent close to your desired pH. Then use equal concentrations of acid and base. Okay? So we are going to calculate the pH of a half liter of buffer solution composed of formic acid. So this is formic acid here, which we're going to call HA. That is going to react with buffer solution. Okay, so we're going to have, I guess we're not going to, yeah. So we've got our HA here. We've got, okay, before and after we add that. Okay, so our HA is going to go in, and we're going to figure out for that, just that HA, that's the formic acid here. We have our H plus, we're trying to figure out pH, right? So if we're trying to figure out pH, what part of this are we solving for? Yeah, right here. We're solving for that concentration, okay? So I'm solving for this. Oops, I guess I shouldn't do that. H plus is what I'm solving for. That's going to equal my Ka, and I gave you the Ka right here. Did I type that into your paper?
Yeah.
Okay, good. So my Ka is right there. So that's 1.8 times 10 to the minus 4. Then I have to figure out which one of these is my acid and which one of these is my base. Acid goes on top, base goes on bottom. So in my buffer, which one is the acid and which one is the base? It should be fairly obvious. Yeah, the one that says acid, right? Okay, so that's 0.5, and this is going to be 0.7. All right, because if we have this is our formic acid. It's going to be in water. It's going to make H3O. No. Bad lippy. Yeah, that's right. I had that right. Yeah. It's going to make H, or wait a minute. They said Na. They said Na. So it must be N with Na something, huh? Sodium formate. So it must be making Na. So this is Na A here, A minus. Oh yeah, so I'm right. Yeah, that would be H3O plus then. There we go. Okay, that makes sense. So these two are going to go together. Okay, because there's your negative ion. So remember, this is just going to end up forming that. Okay, and then the hydrogen from this would have been donated to the water, which would have increased this, thus increasing your H. Okay, all right, we got that now. All right, so now we can figure out our H plus concentration here. I'm just going to divide these two values and multiply by this. That's going to equal my H plus ion concentration. So when I do that, what, honey?
Do they have to be in moles?
No, this is molarity. This is moles. Now, when we get down to the next section, okay, where we're adding in HCl.
Then we turn it to moles.
Mm-hmm.
Okay.
Okay. But right now, we can stay with our molarity. Okay?
Okay, yeah.
All right. So I am here. I've got this point. I'm 2.9 times 10 to the minus 4 molar H plus. But that's not what they wanted to know. They wanted pH. So what do I need to do to this guy?
Negative log.
Negative log. When I do that, I get 3.89. Now, we are adding in hydrochloric acid. Do you expect this pH to go up or down?
Up. Down.
Why?
Because it's a strong acid.
And the more acidic we get, the lower the number we get. Okay, now you got your brain wrapped. We're ready to rock. Okay? Now, here's the beauty of this thing, okay? Here's the beauty of my method. With that Henderson-Hasselbalch equation, the one that they give you on your sheet, okay, you have to turn this stuff back into molarity. With my method, you can leave it as moles. So let's figure out the moles of each of these. Figure out the moles of each of these. How many moles of this guy do I have?
1.
How many moles? 0.5 times.
Oh, 0.25.
Okay, there we go. Now, okay, good. That's what I thought. I'm like, is my math wrong? I didn't think so. Okay, so there's my moles. Okay, what about my bottom?
Okay, where did the 1.86 come from?
Oh, it's supposed to be times 10 to the negative 4.
Oh,
I'll rewrite it. I'm sorry. That's my KA. Good call.
I was just thinking.
Nope, you're good. Don't close this bracket out here. And that really shouldn't have square brackets because it's not really molarity. Okay, what's my bottom value? 0.35. Does anybody not know where I got 0.25 and 0.35?
No, I know.
Okay, so we took, come on, why are you not erased? Oh, you did erase finally. Okay. We took the here and multiplied that. So my moles, remember molarity times liters gives me moles. Okay. And then here, my molarity was this times liters. And that gave me my moles. Okay.
And you're not using concentration?
Nope.
Where did you get?
That's the beauty of my method. Okay.
Where do you get the 6 from? 1.86. And then 1.8.
Oh, okay. All right. Anything else?
What is
Still your favorite class?
Of course.
What are you gonna find right now? Are you gonna find the
What? Yeah, we're trying to find this guy right here.
I thought we got concentration.
But now we've added acid to it. So this is the second part. Before, that's here, and after we've added this. Okay? All right. So now I'm pens. Now I am adding acid to this. Okay? How many moles of acid am I adding?
0.01. 10.
0.01 moles. This, this is 0.01 liters, right? Times 1 is 0.01. Okay? Now, here is how you do the method. Are you listening? This is an acid, right? This is a strong acid.
So you added that.
So we're going to add it to the acid. And we're going to subtract it from the base.
Does that like cancel out the addition of 10 milliliters or something?
Yeah, it's buffering it. Okay. So if I'm adding in acid, right, I'm adding in more of this, it's going to shift and form more of this stuff. So I'm adding this, remember Le Chatelier, if we add some of this stuff in, it's going to shift that direction and form more of this. If I form more of that, it's taking these hydrogen ions out of that solution. So it's pulling them out and making, that's why it's buffering. That's why your pH is staying the same pretty much, because you're not really changing it a whole lot.
What are you adding into this?
You're adding in hydrochloric acid. So you're adding in H+ ions, which is going to shift, yep, it's going to shift and form more of this material here, thus not impacting your pH a whole lot.
Why do you subtract 0.01?
Because it's taking away from this. If we're shifting this direction, ladies, I warned you.
L move. Me? Yeah. That was
If the base is on the bottom, right? Look at your, hey, pens, figure it out. The base is here. This is your base. Not when we're talking about a buffer. Remember, the buffer is a weak acid and its conjugate base. This is the conjugate base. Okay, So when we throw that acid in, we're throwing H plus in there, right? We're adding in this HCl. This HCl is my H plus ion. It's going to grab a hold of some of this conjugate base, and it's going to form this guy. So I'm adding in, I'm increasing my acid, and I'm decreasing the concentration of this guy, or the moles of this guy. Now, in the other method, you would have to then go back, add up all of your volumes, go through and figure out what the new molarities were for this. That's why my method works so much slicker than having to deal with all of that. Does that make sense? Okay, so do the math here. I have my 1.8, Jacob, times 10 to the minus 4 over, and then we're going to multiply that by 0.26 over 0.34. And I guess I shouldn't use those square brackets. Honestly, I'm sorry, y'all. I don't want you to think that that's really concentration. And then that's going to equal 1.4 times 10 to the minus 4 molar what?
Of H plus.
H plus, right. That's not what they wanted. They wanted
pH, so negative log.
Negative log, and that's going to equal 3.86. And as we anticipated, the pH did go down a little bit, but not a lot.
0.03%. 0.203.
Okay, yeah, I don't know if that's how you do it.
Yes, it is.
I don't think, you don't,
Point
I don't think we
3.89 minus 3.86.
and you don't put a percent behind it.
Well, that was an accident. You could actually
All right. Yeah.
the pH.
How did I get the pH? Take the negative log of the H concentration.
What if that's the H instead of the H3O?
It's the same thing. H plus and H3O plus are the same things. They're synonymous to each other. We're just lazy and we don't write all that out. Okay, so now we're going to talk about how we would prepare a buffer solution. Okay, so to prepare buffer solutions, use a 0.1 molar to 1 molar solutions of reagents. Choose an acid whose Ka is near the H plus concentration you want. So the pKa should be close to the pH. So when you're preparing these buffer solutions, look for, if you're talking about acids, look for a pKa that's close to the pH that you want. And then adjust the ratio of weak acid and its conjugate base, and like I said, the conjugate base, the salt, to fine tune the pH. So here we go. We are using acetic acid here and sodium acetate. They want to know what the ratio of the acid to conjugate base will be in order to maintain a pH of 5. Okay? And then how would you make such a solution? You need to know for this problem what the Ka value is. I added that to your notes, right?
Yeah.
Okay. I had a note in here to do that, but that doesn't always mean that I actually do that. All right. We have acetic acid. This is going to be our acid then. This then is going to be our conjugate base, or our base, if we want to think about it in terms of, our equation that we're using. So we need a pH of 5. So I'm going to turn that into my H concentration. So my concentration of H is going to be what?
10 to the negative 5.
What? Yep, 1 times 10 to the negative 5. Okay. So the way we figure that out is we take 10 to the negative 5, and that gives us our value. So 1 times 10 to the negative 5 is our concentration. So that's that side. We know that our Ka value is 1.8 times 10 to the negative 5. And we're trying to figure out this ratio of A to B. So we're trying to figure this out because we're trying to make a buffer solution. So I want to figure out this ratio. What am I going to do?
An equation.
I have an equation.
Divide by
See?
1.8.
Yep, I'm going to divide this. So I'm going to divide both sides by this value. And that's going to tell me that my ratio of A to B is going to equal 1 over 1.8. Right? Because when I divide these out,
The bottoms cancel.
So let me just show you that. Okay.
It makes sense.
So if I divide both sides by this guy, this will cancel. Oh, I didn't do that right. This is 1.8. Okay, now this and this are going to cancel, aren't they? Right? That part cancels, and that leaves my ratio of A to B equal to 1 over 1.8.
I'm understanding.
Okay. So
I already had it ready.
I'm going to mix in 1 mole of acetic acid with how many moles of sodium acetate? 1.8 moles.
Because that's the bottom number. Obviously. Sorry, Allie. I'm bad.
And as long as those are in that ratio, it doesn't matter what volume I have because the molarities then will stay the same.
Yeah.
And however, you know, water you need to obtain necessary volume. Does that make sense?
Can you just like overview exactly what you did, like not just like what happened?
Okay, so my equation is H plus equals Ka times the ratio of A over B, right? I identified that I needed a pH of 5, which means my concentration here is 1 times 10 to the minus 5. If you take 10 to the minus 5, that's what you get. Okay? That is equal to my pKa, 1.8 times 10 to the minus 5, times the ratio of A over B. I divided both sides by this. So divide 1.8 times 10 to the minus 5. I divided the same thing over here. So this, I divided it out because I divided both sides by it. You see that? Yeah. And then if I'm dividing this, I mean, you can put it in your calculator if you want, but you could also divide, take that out, and then that goes away too, because they divide out. So that leaves you with 1 over 1.8. So that's how we got our ratio of acid, which was the acetic acid, to base, which is the sodium acetate. Yay? All right. It is the relative moles, number of moles of the acid and conjugate base, or base and conjugate acid, that is important, since they are the same solution. They're in the same stuff. They're in the same volume. So that's why using our method, this method, you can use moles and come out with the same answer, because the volume is the same. They're in the same stuff, right? They're in the same container. So the volume isn't going to be changing. This allows companies to make very concentrated versions of buffers and just let the customers dilute it. It doesn't matter what the volume is, as long as you have the right ratios. Like here, it doesn't matter how much water we add in, we have the right amount of moles. As long as you put the buffer stuff in there and then you add the stuff to it. They have all of this together, the sodium and the sodium acetate, I'm sorry, the acetic acid and the sodium acetate together in the same stuff. And so you can add in whatever volume you want of water. It doesn't matter, because the moles are in the right ratios. All right.
We can't start. We only have 3.
Good point, no?
All right. I want you to try. I know. I want you to try exercise 3 and 4. I just want you to try it. Okay. All I'm doing is asking you to try exercise 3 and 4.
Yeah.